All right, everyone. I'm Sam Charrington, founder of TWiML, and for this Solutions Guide Spotlight video, we're going to dig into the ClearML product with Moses Goodman, co-founder and CTO of Allegro AI. Welcome, Moses.
Welcome, Sam. How are you?
Wonderful. Looking forward to digging in. Let's jump right in. Tell us about ClearML.
So, ClearML is essentially an open source platform that starts from the development process, goes through orchestration, scheduling, data management, deployment, and recently even serving as well. Um, Everything is open source, and it really tries to make the machine learning development and production into something like CI/CD for software development.
Dig into the open source aspect of the product a bit more. Is it open core with an enterprise offering built around it, or what is the model?
Okay, so essentially everything is open source. So really client side and server side. So you can run your own server, including everything. That said, we do have some offerings for enterprise solutions that are not part of the open source. They are open core. So if an enterprise company is a client, they have full access to the code itself, so they can build on top of it, even if it's not part of the open source that is publicly available.
And are your users primarily operating within their own data centers or in the cloud, or is the solution
So
agnostic?
yeah, so this is a very good question. So actually, we have a variety. So we have users doing hybrid. Cloud is probably the most popular due to cost reductions. But we do have full cloud and full on-prem, depending on the type of data usually that they're working on. And based on that, that's how they set up their servers and also obviously compute, etc.
And how opinionated is the solution with regards to integrations and frameworks and that kind of thing?
So actually, none at all. We try to integrate with all the frameworks that are out there. If we missed anything, then usually the community helps us integrate. And the idea is that the integration itself is as automatic as possible. So the integration is only 2 lines of code. You basically import the Python package and you initialize it. And it does everything that it can in the background to siphon all the information from the frameworks that you're using so that you do not need to manually connect and integrate your code. That means that every piece of code that you have can be very quickly integrated with the system. So you have full transparency and visibility into what's going on inside your different steps in the processing pipeline, development, etc. Because at the end, that information is always accessible from anywhere, and then later can be automated.
Awesome. So can you show us these 2 lines of code?
Yeah, so let's do that. Let me just see if I can share my PyCharm screen so we can do exactly that. So I have here, can you see my screen? Let me just zoom in for a
Yes.
bit. It might be easier. So this is just straightforward TensorFlow Keras example, training on MNIST, obviously a toy example. The only addition that we have here is this line of code. Obviously, we also import the package. So that's the second line. And the other is basically your traditional Keras model and TensorBoard. So what's going to happen is I'll be running this code. What it will be doing in the background is it will connect to the backend itself, authenticate. So the authentication file is stored locally. And it will basically log everything that it's doing. So starting from the code itself or the Git repository that I'm using, including the uncommitted changes because we're all messy while we're developing, hyperparameters that we're using, so argparse, etc., automatically siphoned, all the logs that are reported, so think TensorBoard, Matplotlib, that kind of stuff, console outputs. And also the models that are stored are automatically logged by the system. So at least I know what I did. So once the system is done, I'll get a link to my code that is running. Let's see if we can open that link. So this is probably done. So switching back to the UI, we can see the experiment that we just executed, so we can see the full code itself. So if this is without running script without GitHub, then we'll get the full copy of the code. Same goes for Jupyter Notebooks. If we have a Git repository, we'll get a link to the Git internal Git repository, including any uncommitted changes. We also have a log of all the packages that we used automatically, meaning in the current virtual environment that I'm using on my machine. And also I have all the configurations, meaning arguments that I'm using, df-defined, general configuration files, etc. And obviously I have my outputs, so a few points from the tensor board and some 3D plots, because this is what it was reporting. And with that, I have everything that I did logged into one place with as minimal as possible in terms of integration and effort on maintenance. So everything that I do will automatically appear here in real time. So I don't need to worry about it. I can still use my TensorBoard and my Matplotlib and any other Jupyter lab that I'm using. The idea is that I'll always be able to trace it back, share it with my colleagues, and have better visibility into the development process itself.
Mm-hmm. And so all those values that you're surfacing there are automatically pulled in from the runtime environment. If you want to specify specific values, can you go beyond those 2 lines of code?
Yes. So you can add as many parameters as you like from anywhere in your code. So you can add more configuration files. For example, this one is a custom one. You can add that one because this is part of the setup that you're using. So it'll be logged here. Same goes for any other dictionary of parameters. So for example, if you're using Jupyter Notebooks and you don't have arguments, you can add any configuration arguments or objects into the logging system itself. And obviously you can log manually any other scalars or plots that you want instead of the automatic interface.
Great. So that's a quick high-level overview of using the products. Let's maybe dig into the components.
Sure. So this is basically the first step. So the first step is, how do we create a job in the system? So we just demonstrated how any piece of code becomes a job in the system. Once we have that line here, that means that we have everything that we need in order to replicate that job. So we have the arguments, we have the setup, we have connection to the data, and we have the Python packages, and also the even have the Docker image itself. So the next step is, how do we duplicate it, and how do we make it a part of the orchestration itself? And that actually connects to the different engines that we have in the system. So we have the orchestration and scheduling system that allows us to take those jobs and put them into a scheduler on top of any hardware that we like. So it really separates between the scheduling process, where we want to allocate a resource with priority, etc., to the resource itself, meaning the actual hardware. So we can do any hybrid cluster in terms of compute. So I can have an on-prem machines connected to the cluster, as well as a Kubernetes cluster, as well as bare metal on the cloud, without me as the user having to worry about where my code will be executed, because it's fully abstracted by the orchestration solution, essentially putting it into execution queues, and those execution queues control the priority and abstracting the hardware itself. Then on top of it, we have the different applications that use that mechanism, basically using the ability to automatically schedule things, change them, and send them for the next steps. And that's, think of it as your pipelines and your DataOps, meaning automating processes that are more data-oriented, etc. And we'll get into that maybe later. But the idea is using those abilities allows you to build your own pipelines and workflows on top of it. These are just applications that, sample applications that we provide, but you can always build your own.
Mm-hmm. So the first look at the product was from the perspective of the data scientist, someone who's setting up the jobs. What does it look like from the perspective of the MLOps person, ML engineer, someone who needs to scale this?
So if the data scientists are creating the jobs themselves, Then the MLOps is all about automation, creating pipelines, etc. So what I'll demonstrate now is how a pipeline actually is executed in real time. And then obviously when everything that I do in the UI, the pipeline does automatically for us. So basically programmatically, I can do these same things and have logic built into it so I can better control this entire flow. So for example, what I will be doing now is I'll take my fully executed code here and I will just clone it, which means I'm creating another copy of the setup itself. So now everything is editable, right? So I can go here and I can edit even the code itself. I can even edit the Python packages. If I missed any, I can specify a specific Docker image or parameters if I need to. Mm-hmm. In our example, what I'll do is I'll change some of the arguments. Yeah, let's change the number of epochs to 6, for example. And once I'm happy with the new settings, I can send it for execution. So sending for a job for execution is essentially putting it into an execution queue where we have multiple execution queues. They can be on-prem. They can be can implicitly say something about the hardware itself, for example, like the type of GPU or a number of CPUs or where that hardware is located, specific cloud providers, etc. But it allows us to be totally agnostic in terms of automation and interface. So for example, tomorrow I switch to another cloud provider, from the user perspective and the automation, it's basically totally transparent. I still put it into the same execution queue, and then another machine will just pick it up for me. So what I'll do now is I just put it into the default execution queue. So if I switch into the cluster management part, I can see that I have a single machine connected to my cluster. Obviously, usually we have more machines. This is a demo account. Mm-hmm. And I can already see that this machine picked my job. It's listening to the default queue. And if I go into the queue section, I can see all my queues. I can see different priorities, different jobs waiting in queue, and I can even reorder them so I can control the priority per queue or per set of queues. So now it's installing everything inside a specific Docker, probably the default Docker, because we never actually specified any specific Docker. So it's setting up the environment, it's cloning our code or putting our code into that specific environment, installing all the different packages that we needed, and it will write back on the task itself the entire setup, so we can always replicate it package by package. So originally we only had the package that we used. Now we have an entire copy. So we have full reproducibility of this model, because we want to have the ability to trace back every model, which code base created it, parameters, data that was used, etc., so we can better debug and better understand how to create a better a model in the next time. So let me just jump
every
back.
Model that's created in the training process get its own Docker container that is persisted in the system?
That is a good question. So in order to avoid the Docker mess that comes with creating a Docker per experiment, which means that you end up with thousands very quickly, what we do is we reuse them. We call it base Docker image, which means think of it as the base one as the one that you downloaded from Docker Hub from NVIDIA, for example, like base drivers, packages, etc. And then in runtime, we only install the difference, which means just putting the code into it, maybe some other packages that we're missing, or different versions, and then we run it. And that way, you still have the ability to have your own custom Dockers, but we're not spending storage on just Docker images that were only used once. Sure. We also introduced a lot of caching, so this process of setup is only about 15 seconds to set up a Docker with everything, because everything is actually cached.
And does the MLOps owner have the ability to set up multiple of these base Docker images, say per team or project or what have you?
Correct. So per task, you can specify the Docker image that that specific job will get. So for example, in this one, since I never specified one, it received the default one, which in this specific setup is NVIDIA CUDA 10.1, which the MLOps or DevOps engineer can control. But if I create another clone of it, I can override it with any other Docker image. In the new version, you can also specify some setup bash script that will be executed when the Docker is first spin. So you can have more control and you really try to avoid another copy of the Docker with only a single apt-get package that is missing. And this is, for example, one of the features that we received from the community that actually demanded that because they said, hey, it's already there. Just give us that specific ability. And that's exactly why we added it.
Mm-hmm.
So now I think it's almost done running. So we can also see that it fully monitors the machine itself. So we have full resource monitoring. So GPU, CPU, everything that's going on, updated live. So once everything is done, we will be able to see the models that are produced by the remote execution. So if I click on the model here, so I can see that use an input model. So I can, again, trace back the initial weights that it was using, but I can also use the output model later if I want to go into deployment. So this is the output one. Also, in a second, it will be done, and then we'll be able to actually download the model itself. And all is done without the code itself being aware that the models that are stored locally are automatically uploaded. So again, I don't need to do a lot in order to move from the development stage into the automation, into the MLOps stage, and then vice versa.
Right. Looks like the data scientist doesn't have to necessarily be aware of Docker or maybe even Git, if I heard you correctly. Some of the Git versioning is done in the background or can be done in the background as well.
Correct. So even the Git versioning itself is done in the background for you. So as long as you're working on Git, it will just know it will automatically catch your uncommitted changes. So if you forget to commit your changes, it's fine. We'll be able to restore the entire local environment on the remote machine so you can run with your own magic numbers and whatnot that you changed locally because that worked best up until full production. It's all fully stored. No one can touch it. So this is almost as good as the version control in Git. And now we can, yeah, please.
I was just going to ask about, we've been talking a lot about Docker. Is there an assumption or requirement or compatibility with Kubernetes as the underlying container orchestration system?
Yes, of course there is, but it's not a must. So actually everything is built in a very modular way. So even Dockers are not a must. So basically you can start with virtual environments or Kona environments if you're not a Docker fan or it does not work in your specific setup. Then you can move into Dockers. Then you move into installing agents on bare metal machines, and then you can connect that into a Kubernetes cluster, whereas the Kubernetes is spinning the Dockers for you on your cluster. And then you can do even more complicated when you have multiple multiple Kubernetes clusters managed on top of this system, basically connects to the system.
That's a nice kind of path of increasing sophistication / complexity.
Exactly. So we want to make sure that we cater for everyone, beginners to the most advanced users. So now what we can see that we have the final model here ready for serving with actually everything inside that specific model. So the network itself is stored and we have configurations and we can add labels if you want. And the entire model itself is actually stored in the system, but can also be stored on any other storage solution, which is important for the system to separate the storage from the management. So everything that is done in the background is actually management, not essentially storage. And that will connect maybe later to the data aspects of the system or data management aspects of the system. The system itself will never actually store the data itself. It allows our users to use their current object storage solutions and just introduce the missing ingredient, which is kind of the control plane and management on top of what they already have.
So you've got a model URL there. So the system's created an endpoint. Is that intended primarily for test rapid prototyping, or is that ready for production?
Right. So this is still the intermediate result where you use it internally. And then the other part is what we call the ClearML serving that actually spins a service on top of it, listening to those models that are generated automatically. And then what it does, it's actually like a sidecar next to a serving engine, for example, like the Triton serving engine. And what it does, it listens in the background to change sets in the project itself. So let's assume I publish this model here. So once I publish it, it will automatically detect that a new model or a new version was published, and it will automatically reconfigure the Triton serving engine, fetch it to the Triton serving Docker itself. So I don't need to worry about it. Once I spin the service, it will constantly keep my Triton server up and running and updated without me having to manually update it with the Triton API.
And do you have any kind of control over how that's done in terms of, rolling deployment, blue, green, canary, all that kind of stuff?
Correct. So you can control how many versions you store. You can control which exact models you want to spin there. And you also have full control over canary, A/B testing, etc. when you're using the KF serving engine instead of the Triton bare metal engine. So you need another layer, but this is still built into the ClearML serving offering.
Great. So we talked a little bit about the data science persona, and we transitioned into DevOps. Tell us about the collaboration model.
Right. So the idea is that ClearML is kind of the hub of everything. You can think of it as, in a way, what the software version control is for CI/CD in traditional software development. This becomes the hub of everything when it comes to data science, because as opposed to traditional software development, where the version control actually stores everything that we need, when we think about data science, we need to not only connect with the code, but also with the data and the parameters of the specific model, training, inference, etc. And that's exactly where this kind of experiment management solution as a hub comes into play. Everything is visible to everyone. So the developers actually have an overview of what's being served and used in production. The ML engineers have the ability to constantly moderate what's going on in the current development and insert that into the next generation or next versions of the pipelines. And the DevOps, they have full visibility on the resources that are used either in development itself, because nowadays development is actually quite resource heavy, training models, testing them, etc., but also in production in terms of the resources and utilization that are used in model inference and usage itself, with all the different metrics and use cases and usage available to everyone with REST API and Pythonic API. So you can actually build your own dashboards on top of it and create even better visibility for your own organization.
Okay. We've talked about some of the broad, integrations. Are you assuming Python as kind of a base level requirement?
At the end, kind of, yeah. I guess it kind of rules this entire field. So there is a full REST API, and you can connect to it. So on application level, you can definitely build your own applications on top of it with REST API, especially when it comes to creating your own dashboards and integrating with the system in terms of automation, etc. So for example, things like triggering a pipeline from your own web application. So REST API becomes very easy. You basically have a specific job, you clone it and you send it for execution, and you have the entire pipeline triggered, and you can always monitor it. But if we think about more of a development integration scenario, then currently it's mostly Python basically. So yeah.
Got it. Got it. So you've got some customer logos here. Are there any particular use cases or verticals that you know either are seeing particular traction in, or you're seeing particularly strong fit in?
Right. So I think that the first adoption was from customers with needs in deep learning, mostly deep learning, because of the complexity of spinning GPU instances, managing them, introducing orchestration, scheduling, and priority on top of it. But these days, we actually see this broadening into more traditional machine learning scenarios, where even in machine learning, you want to have that flexibility of some on GPU, some on CPU. Things are getting more complicated, meaning it becomes it kind of overflows the scope of traditional Jupyter notebooks, and you have to have more automation and pipelines. And we see more of those coming into our platform, looking for solutions that are really can encapsulate really the end-to-end, from storing the data itself that we recently introduced into the automation. And over there, it's usually Jupyter notebooks and pipelines built on top of them, which are transparent in the system. So even Jupyter notebooks, you don't actually have to store the notebook itself. By the introducing those 2 lines of code, the Jupyter notebook is converted into code. So it really saves you the time of managing the Jupyter notebooks inside your Git repository, which is a huge value for traditional machine learning companies.
Great. Any final points you want to close us out on?
I guess what's important is the flexibility and the open source of the system. So even if you find something that is missing for you, you can always build it or talk to the community and ask if someone else built it. You'll be surprised to see that how many people build their own things on top of it, just because it's fully open source and that they can actually have that flexibility. And I guess the other thing is the flexibility in terms of hardware management and the ability to actually integrate the on-prem resources with the cloud resources is a huge value for a lot of our users, because that means that they can really reuse the Office resources, as well as kind of move into the cloud without paying a lot of price or any price in terms of development, because the system actually abstracted everything from code through data. So it's just essentially just another instance running their code.
Great, great. Well, Moses, thank you so much.
A pleasure. Ciao.